Yeah, so I'm going to maybe repeat a little bit the last part from yesterday. Maybe try and do it more clearly. Yeah, so this is what we did yesterday, but let us do it a bit differently. Let's just describe the kind of what's the principle. The principle is that or the starting point is a rational number from which we draw the vertical geodesic, right? The geodesic that goes from that rational number to infinity. But then we orient that geodesic from infinity to the rational number, and consider the sequence of Faraday edges intersect that the geodesic crosses on its path from infinity to the rational number. Well, the first thing to prove would be that there's only finitely many edges that one crosses that way. Let me not stop right now to explain why. Let me take it for granted, and then maybe at the end we try to argue why there's always only finitely many Faraday edges that are crossed. Okay, and then once one believes that there are only finitely many edges crossed, then one is easily convinced that the crossings happen in fans, right? So where here we have the first fan, and then at some point there may be, there is an alternation of fan, and then at some point there may be some other alternation, etc., until one arrives at the rational number. Yeah? And then if one takes just that combinatorial information, then one can produce such stripe where formed by just saying, okay, so here we have a fan with two triangles, so just put a fan with two triangles, just two planar triangles. That now don't worry at all about the hyperbolic geometry, and then I'll alternate them as you saw it while going from infinity to your rational number. Yeah. Okay, that's the first thing. The second thing is that since in the sequence of edges crossed, one came from infinity, and then one really had one vertical edge not crossed by the geodesic, which, if you think about it, is the vertical geodesic that in general passes through the integral part of the rational number, the one that is not crossed. Okay, now taking that into account, one sees then that one has infinity and then an integer, and then with the edges crossed. Like, for instance, here the first edge is this one, which is part of the first fan. One knows that this other edge is the naive sum of the two previous ones, and then one knows that then the next one, for the next crossing, the unique new vertex is then the naive sum of in this case of this one, and so on, right? So the next one, the new vertex is the naive sum of these two, etc.
But so what is the criterion for choosing one geodesic instead of the others? So why do you choose the geodesic from 0 to a half instead of the one from 0 to 1?
Okay, so let me maybe mark them in some color and then yeah. So yeah, so 1 second. So so you say in going from this crossing to this crossing, why do I choose this one instead of this other one?
No, instead of
or
one
what?
on top of it.
So let's see. Okay, so let me maybe go back. So I'm coming from infinity, yeah, parallel to the unique one that I'm not crossing at all in the whole process, and so I have the first crossing point, and then I realize that crossing point is between your geodesic and an edge connecting a vertex that you already had considered and a new one. So let's say yeah and a new one, and then I realize that the new one is the naive addition of these two. Okay, now and then I consider this one to be taken care of already, and then I go to the next crossing point. But now the next crossing point is this. No? And then I don't know if I answered the question because somehow I did take it into account. No? Okay. Is that was that the question? Did I understand correctly?
Yeah, exactly.
Yeah. So it's like I did take it into account, and then in the planar depiction, this one is depicted here, and then I'm coming from infinity, and then this is the first one, which is this one, and then and then I label this other vertex. I mean, here you have these two, and then I label the other vertex, which is this one. So I label it with the naive addition. Yeah. But then I so somehow, if you want, let me say so. Here somehow I already justified why this one is labeled with the naive addition. Because so far I only told you draw this stripe by just taking certain fans, certain alternating fans, and gluing them. But I haven't told you why I put these labels, right? So somehow these labels, let's say, they come from I always put the two labels. So I always put infinity and the integral part of the rational number, which in this case the integral part is 0. Yeah, but then hopefully I did understand correctly your question, and then I continue with the next crossing, and for this next crossing, which now is between the geodesic and between the vertical geodesic and this, bless you, and this Faraday edge, I noticed that this Faraday edge has one of its vertices is old, and the other one is new. So and then I realized that the new one is the naive addition of this old one and somehow the previous one from the previous crossing. So from the previous crossing and the other edge and the previous crossing. So it's the naive sum of these two. So that's why I put 1/2 here. And so on. No, I mean, let's say let me do one more. So the next one is actually this one, and then somehow I realized that okay, let me draw in like a I don't know, this sort of magenta to say this one was considered already, yeah, and now somehow well, yeah, this was considered, and then the next crossing, and then I realized that the crossing happens at a far edge. Yes, and one of the vertices of the edge was already considered, and the other one is completely new. Actually, sorry, not considered. What's already? Let's say already considered, and the other one's completely new. And then I realized that the new one is the naive sum of the other end with the one from the previous crossing. From the kind of like this new one is the naive addition of the other end of this one, naive addition of this one, and the other end of the previous edge. That's the thing. So I would be saying this one, the new one, is a naive addition of the previous one, of this, because it corresponds to this crossing, and the other end of this previous one. So this one plus this one, and so on. No? My point is that now somehow in going from left to right, every time I have I already have something labeled, and I'm going this way. What I have is the opposite vertex, and this opposite vertex has to carry the label naive addition of these two. So in the end, the algorithm to label the vertices is straightforward. And what I did was kind of to justify that it corresponds to the actual rational numbers that appear as vertices of the edges crossed by the geodesic. Okay. So, for instance, another one. Let's say that now you give me, this is the rational number. So I begin with 67 divided by 24, and then so first, at this point, to be able to produce this picture, I really have to first look at the hyperbolic plane, see the fans, and then draw the fans. And once I draw the fans, somehow, if you want, after drawing the fans, what I have is only this information. I don't even have this, right? So I looked at the hyperbolic plane, at how the vertical geodesic crosses the fiery edges. I produced from the combinatorics of those crossings. I produced this stripe. And now I have to start labeling. And now I know that I start from infinity. This one is infinity. And then the next one has to carry the label integral part of the rational number. So this one is what? Is 2, no? Because it's 48. Yeah. So it has to be 2. And then I know that then every time I already have 2, then the opposite side has to carry naive addition. So this, and then these two give me naive addition, and then these two give me naive addition, and then what? And then these two give me naive addition, etc. And then I populate this, and then because I began with the geodesic going from infinity to the rational number, and from there I read this stripe. I know that the very final point has to carry the label, the rational number you started with. So from the construction, I know that what that the last one has to carry this one. And actually, if we draw the geodesic only combinatorially, the geodesic goes from infinity to your rational number. So that would be like, let me do it like this. That would be kind of just combinatorially written. Yes. Okay, and then I just start doing certain observations, which are like let me do it kind of slowly now, just to be completely clear. So I'm repeating a lot of what I said yesterday. So I know that this is a 2. So let me this one kind of put this, because this is the integral part, so it's a special one. But okay, and then I notice the following. Here I wrote this as a naive sum of these two. Yeah. Right, and then because right after, because somehow when I consider this, what I'm considering is this crossing. I just write this as 2 plus 1 divided by 1 plus 0, but then I write it in this way and record the 1 in a box, just because there is a change, an alternation in fans here. And then I continue, like 5 halves, a naive addition of the previous 2, but it's naive addition of 2 1, which is the previous one coming from the previous crossing. So now I am at this crossing, but from the previous crossing, plus 3 1, the other one. Which now I write like this. You kind of just humor me. Okay, now it starts becoming more interesting when I go to the next one, because here I have to take the previous one, 5 halves, which is this. Yeah, naive addition with again 3 divided by 1. Okay? So the previous, this one, so let's say, so this one has to be this one plus 3 divided by 1, and then I notice that it is not coincidence that there's this 3 1 and 3 1. So what I do, and then it has to be naive addition. So it's this one plus 3, this one plus this one. So I just write it this way, and just noticing that it was not a coincidence that I was able to just put a 2 and a 2 here when there was a 3 and 1 there. That's not a coincidence. Then the next one, for the next one, is 8/3, which is this one, yeah, plus, and again the same one, 3 divided by 1. 3 divided by 1. I mean, and why is it the same one? Because I have been traversing a fan. So that's why it's the same one, the same one, the same one, the same one. I mean, the fact that it's the same one is really the counterpart of not having yet alternated the fan. Okay, and then I know, and then it's this one again plus that one, and then I notice, so it's numerator plus 3, denominator plus 1, and which I can then write like this. Which I mean, it's obvious that I can write it like this, but my point is it was not coincidence that I could. Yeah. And because here there is now a change there's an alternation of fans, I record what I have thus far. I record it in a box, because now I know, since there's a change of fan, now I know that I'm not no longer going to be naively adding 3 divided by 1. Now I'm going to start naively adding the other one. Okay, now here there's going to be only 1, so the alternation is immediate. So I record that 1, yeah, and then I did something. Yes, sorry. You see here I changed this 4 to a 3. Sorry. So here, let me correct it. Yeah. and then and then finally here there is a change. So now I know that in the upcoming fan I'm going to be adding this one naively each step. Yeah, and then adding it naively each step. So it's this here and here amounts to just augmenting or grow, making just the other factor grow by one, like by one step. And finally, I mean, here I'm done. So I record in a box. And then what I notice is the following. So now let's focus only on the ones that have boxes. So I have this one, I have this one here, and this one here. Okay.
Sorry, just a quick question.
Yes.
How to tell when there's a change of fan with only this diagram? Because geometrically, I can understand why when you sort of run out of geodesic starting from the point, but how can you tell, for example, from here that there's three, let's say, triangles in one fan, and you move to the next one, and it's done immediately?
I guess you can. Let me think. Let me do this. Let me draw arrows. Let me draw some arrows. I don't know this. Within each triangle, clockwise. So let me draw like this. I mean, just because I can, right? Which I certainly can in the hyperbolic plane, right? Because the hyperbolic plane is oriented, right? So each triangle carries canonically a notion of clockwise. And then combinatorially, I would say that it's when there's a change of direction in the arrows. So you see, I start here, and then here, this one goes parallel, I mean same direction, but this one goes up in the opposite direction. And then parallel again, parallel. If here I had this, I would say change of fan. But if I had this, then I would say the fan hasn't ended.
Okay, then the question still remains sort of, for example, when you reach 11/4, so you've added 3/1 naively to 2/1 3 times.
Sorry, can you say them again? When I reach, which one?
You reach 11/4.
Uh-huh.
So you've done the naive addition of 2/1,
Bless you.
3/1 3 times.
Yes.
Why do you not add 3/1 again to get 14/5?
No, yeah, I did, but somehow the point is, suppose that here my fan was longer. Bless you. Yeah. Suppose that here the fan was longer. Here I would have to write 14/5. Yeah. But the observation is that afterwards, the one that would be repeated is not 3/1, but this one. You see, let's say here, to obtain this one, I added 2/1 and this. For this one, I still added 2/1 and this, but it's in the next one where you can actually see that the one that is repeated is not 2/1, is this one. So it's kind of, you see the difference starting from the second triangle of the fan.
Yeah. Okay.
That the special one changed.
Yeah, but so then when does the special one change? Because for example, 14/5, you could write it next to 11/4 at least.
Yeah. So the thing is, since I can combinatorially decide where the change of the alternation of fan is, that's where I think. That's when I start thinking, okay, my new favorite one is this one, like before it repeats. You know, like one step before it may repeat or not.
Okay, but yeah, okay, you can combinatorially decide, but the thing is, when I look at the picture, then it's much more obvious when the special one changes because you sort of run out of geodesics starting at 3-1.
Starting at 3-1, right? Yeah.
Because the reason why you change the special one from 3-1 to 11/4 is because the geodesic from 3/1 to 11/4
was the last one. Yeah.
was the last geodesic
Evolving 3-1. Yes.
Yeah.
Yes.
So geometrically it's obvious, but
yes.
I don't know how to translate this obviousness.
Yeah.
Like if we stop at 14/5, why it is not like near 11/4? That's the question. Like,
Yeah, I guess.
there is no-
Yeah, I guess you can say it. Yeah, if you think, you know, here 3/1 is on the left, and then this one is on the right, and then again on the left. So I guess I don't know if it's satisfactory, but it's like when you change from having your vertex from one side to the other, you know. I mean,
Yeah, compared to the vertical line that
Yeah.
starts from the other side.
yes, yeah, but I don't know if somehow that's a satisfactory answer for you.
Yeah.
I guess not. From your face, I guess it's not. But
Yeah, because just from looking at this sort of simpler model, it's hard for me to understand where it changes, even though geometrically you can.
right,
see it
yeah.
Because I was thinking maybe it's like since it changes when you're sort of starting from the other side, then it's maybe got something to do with when the number becomes bigger than the previous number, or when it becomes smaller than the previous number. But I don't think it's.
You know, but this I think this what you said I think may be right. Yeah, but I would need to stop and think a bit more carefully. But I think what you just said is kind of the that's like another characterization. Yeah.
Maybe not necessarily for the one before, but necessarily for the, in this case, the 76. That's the point. Like, I think that because in the example before, there were like the one in the bottom, the one in the top, everything is on the left of
Right. Yeah. Until this point,
all
until
of
this
them
moment.
bigger than, so the one in the top, I think that they are all bigger than
Right.
3
Yeah.
or 8, while the one in the,
Yeah.
and
Yeah.
that is actually when you see the functional,
Mhm.
that's why you put it there.
Yeah. I think so. Yeah.
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 So I think that there is no ambiguity if you stop at 14/5, you put it on the top and not on the right, and not on the bottom, like that one, because it is.
And because 11/4 is 66/4, so it's just smaller than than 67/4.
Yeah.
And then 14/5, I guess if you
Yeah,
do
it's-
the denominator,
yeah,
it
Yeah.
probably
It's
jumps to the
almost
other
3. Yeah. Yeah. No, I guess. Yeah. No, I think that's right. Yeah. No, but I think if one sits down and thinks about it carefully, it's exactly that. I think. Yes.
Maybe
Yeah.
now when I'm thinking about it, maybe the last one maybe has some ambiguity, because before we put the last one on the top, like in this case we are putting 75/24 at the bottom.
This one.
Yeah, the last one, like the one, like I don't know if that is bigger since it is equal at the, I don't know.
Okay, you reach the one that you chose at the start.
Right. Yeah. But you see, the thing is, this between this one, the thing is, it is the naive sum of these two, so it lies in between them.
Okay.
So you only need to know which one of these is bigger, right?
Okay.
But then the thing is, this one is naive sum of this one and this one, so it lies between the two. So it seems to me that this one is maybe smaller,
Yeah.
which means if that's correct, this one is smaller than this one, smaller than this one. If that's correct. Kind of, but yeah, of course, I needed to start going back, kind of going back to be able to decide. But
Yeah.
I think a good way of seeing it is that on the top of the diagram, you have the numbers that are bigger than the chosen one. Yeah. Because, okay, infinity is bigger. Then you go to 2 and that's smaller, so it goes on the bottom. Then you go to 3, so that's bigger, so it
Bigger.
goes on the top. Then you go to 5/2, it's smaller, so it stays on the bottom. 8/3 is smaller, stays on the bottom. 11/4 is smaller.
Yeah.
and then-
Yeah, I think so. Yeah.
Yeah, because I was looking at it like if you consider infinite in the upper, like in the upper, you can like this, like, and the middle, like the green line is like the
Yeah,
one where
it's like a, when does this happen? For instance,
yeah,
it's because your point was always on the left, no?
yeah. So the 1, 3, 1, 4, 5
Mhm.
are always on the
Yeah.
left.
Or conversely, like when does this happen?
Yeah.
It's when your point was on the right.
Yeah, so it should
So this means having a fan like this means that these points are all smaller than your number, and the common is bigger.
Mhm.
But this other fan means the kind of the opposite. But one is one fan like on the right, and the other one on the left. So yeah. So from being a left or right fan, you can deduce the the order relations between them. Yeah. Okay, so now, so what I did was now take boxes. Just single out the rational numbers where I had put a box, right? Which and putting a box came from alternating fan. Now, if you see. Here at the beginning, here I have infinity, so I have 1 divided 1 0, and here I have 2 1, right? So it's the integral part, so it's 2 1 here, yeah, and then after that, I notice 3 1 appears here, and this one is the previous one. And now when I move to the next one, 11/4, I have, what did I say? No, sorry, 3 1, and I move to the next. Yes, so yes, this I already did. Yes, yeah. Okay, sorry. I move to the next one, and then what I have here is the previous one in a box plus the other previous one in a box. I move to the next one, and what I have is the previous one plus the second previous one, and the coefficients in boxes were precisely the number of triangles in each fan, in that order, right? So 1, 3, 1, 4, and then I would say, it's not hard to be convinced that this is a general fact. So in other words, that every time I take my rational number, consider the vertical geodesic coming from infinity, produce the hyperbolic fan, the hyperbolic alternating fans, and then drawing this, and then labeling correspondingly, so that I know that the final vertex is the original rational number. When I do this putting in boxes algorithm, the corresponding sequence satisfies this recurrence relation. You see, and actually, not only that, it's like the numerators satisfy this recursion, and the denominator satisfy the other recursion. So it's stronger than just having this recursion. Okay, and moreover, with certain, you see, the thing is the putting making this observation that is actually that the numerator satisfies certain recursion and the denominators also allows me to say that then for the numerators I take the initial conditions that let's say I begin with this, which would be let's say A0. One second. No, not A0. It would be row 0, and then this one would be gamma 0, and this one would be 1 second. Yeah, row 1 and gamma 1. Yeah. Is that what I want? Yes, it's what I want. Okay. But here what I mean here I want to say that I can also I can say, okay, the initial conditions are precisely, you know, the one coming from infinity, the two coming from the integral part, and these ones are just 0 and 1. Okay, and this is going to become important in a few minutes. Okay, so I know that. So now let's talk about something seemingly different. Here, before talking about continued fractions, notice that here again I have a triangulated polygon and a diagonal connecting points and crossing the triangulation. I mean, similar to what we found at some point in the when we were discussing the Teichmüller space of a polygon. Now, to introduce continued fractions, or kind of like to justify why we are going to do these kind of weird operations.
Sorry, can you put your screen?
Yeah,
sorry.
Maybe if you can. Because it turned off after some.
Okay. Was it already very long?
It turned off after like 1 minute, so that it is.
Okay, so
like,
it's because.
if it is possible, if not,
It's
we
because
just,
no, it's
we
because.
just pay attention and.
Yeah, no, sorry. Yeah, it's because I didn't plug it in.
No, there is nothing. Maybe you are.
Yeah. Okay. So the thing is, the definition of a continued fraction may seem very weird at the first glance, and so what I want is to kind of to justify a little bit, just to demystify the definition. So we all know Euclid's algorithm for computing the greatest common divisor of two let's say non-zero integers. And we know that it builds upon iterating the division algorithm for the integers. No? So let's say that I'm interested in dividing 3 divide 3 by 8, right? So what do? We know, right? So 3 divided by 8, quotient, residue. Okay, and then we know that in Euclid's algorithm, then one takes the new quotient and divides it by the residue. So I take the quotient, divide by residue, okay, and then one obtains a new residue. If it's non-zero, then take the last quotient and divide by the last residue, etc. Right? So last quotient, last residue. If it's not 0, iterate last quotient by last residue, and then we know by because of the division algorithm we know that eventually we reach 0, and we know that the last non-zero residue is the greatest common divisor. And actually, we can start solving, right? Like substituting. Like here, we know that this 2 came from this 2, and we can perform the corresponding substitution, etc., so that one can actually interpret this one, not interpret, but write the last non-zero residue as a Z linear combination of the 2 original numbers. Okay, but let me stop here and then remember. Okay, so somehow I was interested in dividing 3 by 8. Yeah, so instead of going in the direction of the greatest common divisor, I'm going to say, okay, yeah, don't forget that you wanted to divide 3 by 8. Yeah? So divide it, right? So this equation becomes this equation. Yeah, and then of course these inequalities become that this is positive and less than 1, which is anyway obvious because we are saying it. Yeah, but then in the next step becomes dividing by 3. So I write it. Yeah? Okay, and then the next step becomes divide by 2, and then the next step divide by 1, and here that's it. And then here you see, since in the next in any given step in the next we took previous quotient divided by the corresponding residue. What we have here is when we divide this here by 3, this 3 disappears and we have this 3. Yeah, but then this 3 in the denominator is actually this 3. And then here, when we divide by 2, we are dividing by this 2. Which means that indeed, it is not coincidence that here there's a 3/8 and here I have 8/3. It's not coincidence. And then here I have 2/3 and then here I have 3/2. No coincidence, etc. Right? 1/2 and then here 2 divided by 1. No coincidence until I finish, okay? Which is plus 0. Okay, and then well, what I can instead of taking the kind of the direction of solving for this one, I take the kind of the opposite approach and say no, solve for this one using these substitutions. So 3/8, I use the first one. Yeah, is of course this. Yeah, but now the next one tells me that this 3/8 is 1 over this one that I can substitute. Yeah, 8 divided by 3 I can substitute. So I substitute it, and then I have these 2/3, which the next one tells me you can substitute it as 1 by 3/2, which one you can replace. So replace it, and then this 1/2, the next one tells you instead of 1/2, write like 1 over 2 divided by 1. Yeah, but then and then here this one tells me you are done. So this last one survives, and I know that 3/8 can be obtained, from the numbers 0, 2, 1, 2 by performing these kind of nested divisions, right? Like by first to 1/2 add 1 and then take the inverse, and then add 2 and then take the inverse, and then add 0. Yeah, by the process itself tells me when you perform these operations, you obtain 3/8. This looks like it looks like a reverse recursive process. But in any case, the thing is the thing is, if I want to perform the operations, somehow the operations, kind of everything is determined by saying what integers are here, which were, since I took a rational number and originally this one could have been negative, and let's say I take the quotient always positive because the denominator I always taking it positive. I noticed that the first one could have been negative, but all the other integers that appeared are necessarily positive, and were precisely the quotients. The quotients, when I divided 3 divided by 8, the quotient. 8 divided by 3, the quotient, etc. Okay, so if you now give me a finite sequence of integers, the first one of which, well, the 0th one of which may be negative, but the other ones I always take positive, we define the continuous fraction, and we use this notation to be the rational number that you obtain by performing precisely those operations. Like start with the last one, but then take 1 divided by the last one, yeah? and then add the second to last one, 1 divided by that, the third to last one, 1 divided by that, etc. That's what I mean by that. It seems like a reverse recursion, and because somehow one doesn't start with the very first one, but with the very last one, and that's actually sometimes a little bit annoying. So the example that we just saw is this one. So we just saw that 3/8 is the sequence, so 0, 2, 1, 2. So 0, 2, 1, 2, and I just put this semicolon is just to indicate that the 0th one, which is this one, may be negative. 67 divided by 2. Well, you can apply the process of it's not here. No, you can apply again let's say the process of just Euclid's algorithm to obtain this. So I mean, it's pretty much for every rational number, I can apply Euclid's algorithm and obtain such expression, which means that every rational number has a finite expression as a continued fraction. Yeah. Okay. Here another example. Yeah, I don't know. Maybe I'm not going to repeat it again, but it's again, right? I mean, I start with the rational number 41 divided by 23, and I'm interested in expressing it. I apply Euclid's algorithm and reinterpret it and perform the substitutions this way. And here it is. Okay. Okay, so now what do we have? Pretty much by construction, like practically for free, we know that every rational number can be written in at least one way as a finite continued fraction by Euclid's algorithm. So at least one. But it actually happens that every rational number has exactly 2 expressions as finite continued fraction. So let's say okay, for the existence, you see here is like the kind of the abstract process, right? I mean, the kind of the general situation explained abstractly, but it's just what I just said, right? Euclid's algorithm and reinterpreted, and then with the substitutions. Okay, so here my x is s divided by t. Okay, so existence, as we said, is already okay. I just want to emphasize that defining these rational numbers means well, having certain inequalities. that they are important. Maybe I'm not sure they will play a role today. Anyway, so there's existence, which in any case I had already convinced you. And then to produce a second expression, consider, like, for instance, this one, because for example, so let's see what if you see this one, what would you do with this one to produce another one?
May I ask a question first about the statement of theorem? So, just to understand exactly what we're saying. Are we saying that given a rational number as a reduced expression,
yes,
you can have exactly two sequences of length n plus 1?
No. Actually, they don't have the same length.
Okay, so
yeah,
there are only two expressions in general.
Only two.
But the constraint is that the result has to be reduced already.
The result has to be your rational number.
Okay, so not reduced.
Let's say, yeah, I don't care. Okay. Just rational number.
Okay.
You see, because why? Because when I perform the first division,
if there is a common divisor.
Yeah, I think. I wanted to say that it kind of it gets killed. I would need to see a little bit more. Right. I mean, the thing is, this equality doesn't care whether these were prime or co-prime or not. Yeah. So so that's the point. In each of these, it's equalities that it didn't matter whether 41 and 23 were co-prime or not.
Okay.
So in the end, the substitutions will give you your rational number, even if it's not if it was not originally expressed as a reduced fraction.
Okay.
So I want to express the rational number as the result of doing certain weird operations. Yeah, and for each rational number there are two sequences, and actually two sequences of A's, and actually they don't have the same length. And so kind of I would say that if you look at this expression, for instance, for 3 divided by 8, you can see the other, you see this expression is gives you the expression of this one as discontinued fraction. But I would say if you look at this, you see the other one as well.
It's like taking the final two in the denominator and putting in like.
Yeah, so 2, how do I put it? I have to put it as something positive plus 1 divided by something.
Yeah.
So something positive. So that positive has only 2 chances, 1 or 2, because 2 is already 2. Yeah. Plus 1 divided by something. That 1 divided by something cannot be 0. So it has to be 1 plus 1 divided by 1. So this one is equal to 0, 2, 1, 1, 1. But because you see, this is because this 2 is 1 plus 1 divided by 1. So this one is this one. Yeah, let's say this one is this one, and this one is this one. Okay, and then here you do the same, right? So I mean, same thing, right? I mean, 4, something positive plus 1 divided by something, 3 plus 1 divided by 1. So this one is 2, 1, 3, 1, 3, 1. Same thing for the other one. And what am I relying on? I'm relying on the following being truth. The last one is always greater than 1, so that I can perform this trick. Right. So but which one is the last one? The last one, let's see. Abstractly is so what is the last one? The last is the last quotient. Is the last quotient where let me see, where the residue you obtain is already 0. And that one is greater than 1 because you see this one, because this one being 0, an is equal to this, which is the inverse of this, but this one is smaller than 1, so this one is greater than 1. Yeah, is it clear? Because somehow one starts dividing, and then when you start dividing from top to bottom, you do it precisely in such a way that you divide everything by the denominator. By that thing over which you are dividing, and the residue is always smaller than that. So you always have these inequalities of positive and smaller than 1, positive and smaller than 1, positive and smaller than 1, because that's the way you are dividing in each step. You are dividing by the thing you are you are. That sounds silly, but you divide by the thing you are dividing by. Right? So this means and the last one is smaller than 1, but this one, its multiplicative inverse is an, so an is greater than, is an integer greater than 1. So this trick can always be performed. So there are at least 2, and you see they are not of the same length. Actually, the difference of their length between their lengths is 1. Okay, which, by the way, for instance, for a negative integer, what would you do? So, like, for instance, if I say that this is correct always, I have like I don't know, like, let's say -3. So on the one hand, is what is -3 is just -3 because the a0 can be negative, or otherwise what?
-4 plus 1.
Yes. No? So -4 plus 1 divided by 1. So -3 is just 3, or -4, 1. Thanks. Yeah. Okay. And now uniqueness. Uniqueness is a bit of uniqueness requires some element, some like preparation lemmas, and that are actually quite nice. But let me not reproduce here. But actually, Lang does it very nicely in his book. And it's very elementary. It's really, really elementary, the uniqueness. So let me just leave it there. By the way, so here I put it so that I would write that this is equal to a0, a1, an minus 1, an minus 1, 1. Yeah. Okay. And now another theorem, which is like lies in like is one of the foundational theorems that I'm also not going to prove here. Is that consider your finite continued fraction, right? Where, remember, the 0th one can be negative, I don't care, or 0, but the remaining ones, I always take them to be positive. Yeah? If you want, why do we always take them to be positive? Like, one reason is that if I taking them always to be positive guarantees that I can always perform the operations. Like, if I allow negative things, it may be that at some point there's a cancellation or something, you know, and yeah, but and at least a priori. Yeah. So somehow the point about that is that I can always perform the operations. And now this continued fraction, which gives me a rational number. From this, I can extract a finite sequence of rational numbers, namely by truncating the continued fraction. But I can start with a0, and then the continued fraction a0, a1, and then the continued fraction a0, a1, a2, etc. And this gives me a sequence of rationals whose first member is a0, and the last one is the rational number, the rational number I am focusing in. Okay, and the theorem is that when you write them as reduced fractions, then the numerator and the denominator satisfy. Well, first, you know, the zeroth numerator and denominator are a0 and 1, which is obvious because I'm truncating here, and I'm saying just write as reduced fraction. So it's a0 divided by 1. The first ones you can actually see this because you write, you know, for P1 and Q1, you just notice that that a0 a1 is a0 plus 1 divided by a1, which is a1 a0 a1 plus 1, and this is already in reduced form because a1 is a factor of this one, and and then the other one is just 1. So the greatest common divisor of this one has to be 1. So this gives you this numerator is this one, and this denominator is this one. Yeah. And what did I just write here? I mean, this is, yes, sorry. Yes, it's the same recursions that the other ones satisfied, and you see, even if you take that and compare, yeah. For this one, I think I didn't quite write it, but you could see it here, right? I mean, this one is yeah, this one times this one plus 1 and gamma 1. Okay. I'm not going to give you the proof. The proof is really well done in Lang's book. But the book by Levesque also has a proof, but Lang's proof is neater, and I would say it's really beautiful because overall what it does is it defines the notion of a continued fraction for any sequence of algebraically independent variables. So it's you know, like what he does is he starts with any sequence of algebraically independent variables, and the fact that they are algebraically independent guarantees that one can perform the operations without any trouble. And then he starts like doing algebraic manipulations and proves that, and then produces a sequence of polynomials that satisfies the recurrence, but with the variables instead of just the a's. You know, here is x0, x1 here, and then here x0. And then he proves that this kind of formal continued fractions satisfy the recursions as polynomials, and then just sees this theorem as saying, okay, then just evaluate in your n+1 tuple. So it's really beautiful, but I'm skipping it. Right, but then, okay, another example. So here, well, I mean, maybe I don't want to stop too much. Here, this one, you see, again, doing through Euclid's algorithm, you obtain this. So you obtain that the continued fraction expansion of this one is equal to this one. Yeah, and then just kind of to compare, just because I can, I put the other picture that we had at the beginning, and what we notice is that this 2 appears here, and it has to appear. It has to appear because this one has to be the integral part of the rational number. And here we also said it has to be the integral part, okay? And then 1, 3, 1, 4.
Sorry, in one of the two representations.
Sorry, yes. Okay, let's say for positive rational numbers. For the other one, yeah, for the other one, for instance, -3. The problem I have with the integers is that with the integers, the problem we have is that the geodesic is already a Farey edge, right? So, kind of for the integers, one obtains just the very first edge, and all the rest is empty. So somehow this is meaningful for non-integers, let's say. But other than that, yeah, you don't need to assume that this one is positive. It can be negative. Yeah. Yeah. So let's say, but thanks, because let's say what I'm saying is correct. Let's say when the rational number is not an integer.
Because I was wondering when you said that there are those unique two ways of representing any rational number as a continued fraction. To some extent, I suppose you could make a uniform choice from one of the two expressions.
Yes. Yeah. Because
you could say I take the shortest one. Right?
Yes. Yeah. Or the one where the last one is greater than 1. Mm-hmm. Which I think here it amounts to, the last segment. The last segment, you can think that it's part of this fan, or that it's part of its own fan here.
And that was the ambiguity that I was thinking about.
I see.
The fact that in the middle there is no bigger one, and if you put it up, you are the longer sequence.
Mm-hmm.
And that's good.
Yeah. So, but now my point is this we know that it's a general fact, this coincidence, and the rest of the coincidences is because on the one hand we know that the truncated continued fractions, which are precisely these ones, why are they precisely these ones? Because we know that they satisfy the recursion. and we have the same initial conditions. We know that those ones, yeah, how to say? I know that if I consider these integers, what I obtain is precisely the same sequence of rational numbers that I obtain from this one, because I'm going to have the same recursion and same initial conditions. So in other words, what we have been doing shows that these numbers, that the first number here, which is the integral part, has to be the first vertex different from infinity, and then the remaining sequence has to be the sequence of the length consisting of the lengths of the fans. So I would say this is completely justified. I mean, we have a theorem, which then it's kind of more or less stated here. I still really haven't justified why it crosses only a finite number of edges.
I was thinking about that. Maybe that you're choosing one particular vertex of the graph, and it means that that vertex appears at some point of the iteration. And then the edges that these straight line crosses are always finite because they are in the end iteration of the construction, and between two integers there are only finite edges at that point.
Yes, I like it. Yeah. That the denominator, that you know that since in each step you apply a naive sum, and your original rational number has a definite denominator, everything that you crossed must have denominator smaller. Yes. So hence only finitely meant. Yeah. Thanks. And in a bounded interval.
Yeah.
Between two integers. Yeah. Okay. Yeah. So thank you. So. And then here, just once more, what are the places where the changes, the fan alternation takes place are precisely these ones, because look here. The numbers in the boxes are precisely, you see, I mean, in these boxes are precisely 3, 1, 11/4, 15/5, which, I mean, you can, I mean, the formal description is, it's precisely, the result of applying the recurrences. And the places where one has the change of alternation, the change of alternation. One has the alternation is in these ones, right? In these edges connecting them. Yeah. Okay. And the first one and the last one, but the changes are in this. Which then that's what I'm saying here. Yeah. Okay. So one thing is the one consequence is the following. I mean, right now somehow we have been thinking, if you start with a rational number, you can do two things: either apply Euclid's algorithm and produce this, or you can do this hyperbolic whatever trick and draw the strip, and then you also obtain this. Yeah, fair enough. But now, from what we have done, we also now know that if what you give me is just this, is just the sequence, now we can compute the rational number. That you can say, yes, of course we know that we can compute it, but we can compute it in a very easy way, which is just draw draw your graph, draw your stripe with alternating fans, and start labeling, because you know that you start with 1 0 and A0 divided by 1, and then on the drawing on the stripe which you drew using these numbers, you can start labeling using the naive addition. And in the final one, that's your rational number, which is this one.
Okay, so the AIs give you the information of when to alternate.
Yes. Yes, the AIs are these ones, are the lengths. Yeah. So if you give me the AIs, you see, if you give me the AIs, we know that A0 is this one. We know that the starting point has to be infinity, and you know and then what did I do? Yeah, and then A1, and then A1, A2, A3, A4, yeah, and you have the first two labels. So naive addition, 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 and this, the final one, is your rational number, which I don't know. I do think it's simpler than doing all this. No? Okay, let's say that's why I wrote allegedly.
Is there some kind of proof that shows that the algorithm is written in, the implementation of this in the algorithm is actually quicker, like it's so.
I don't know. I don't know if yeah. And that's why I wrote allegedly, because I don't know.
Yeah. I think that for a computer it's much easier to do this.
Yeah.
But then if you have to do it in your head, then of course it's easier to do.
Right. Yeah.
And because the computer doesn't care the difference of 9 sums and adding the inverse of another together.
Yeah. Okay, I mean, kind of on the other side, I would say, I don't know the answer, no, but I think that taking inverse may introduce floating point error, and the other one is you just keep adding integers, because the naive addition is like carried out independently in the numerator and the denominator.
Yeah, we have to do it symbolically, like do the an plus 1 over something symbolically.
Right. Yeah. I mean, you kind of against what I just said, you can say, but integers is not like you can really add them that you can take arbitrarily big integers and put them in the computer. Right? You still have a problem. I mean, so I don't really know. Yeah.
One question that I had in mind before now is my natural class is, do we have some bounds on the elements of these sequences? Like, because the examples we saw are rather simple, right?
Yeah.
All the AIs are quite low.
Yeah.
And I was trying to think in general, and maybe it's trivial, but I couldn't see.
No, there are some. This becomes maybe more transparent when one starts talking about infinite continued fractions, which correspond to the continued fractions of the irrationals, because then you can define in a formal way what it means for a sequence of rational numbers to be the fastest one approaching the irrational, and it turns out that these ones p divided by q obtained by truncating are the fastest ones. So which means that somehow for the rational, somehow the process, maybe my intuition is wrong, but informally what I think it means that for the rationals, the process finishes very soon. But of course, you have you have arbitrarily long finite continued fractions. So what I just said doesn't really make sense. But But it does make sense to think, okay, even if it's very long finite, the truncations approach the last rational number very quickly. That can still make sense, and this can be done formally. Yeah, like this being the fastest, one can give a precise definition. Yeah. Which I don't think I'm going to do it in this course because I'm already behind. So yeah. So I mean, some more examples if you want to play around. I mean, if you want to play around, saying, okay, so let's say I start with this two, and then say okay, so and then on the other hand, do the operation and then really convince yourself that they are the same. That this is actually this. And also don't forget that really in the background, like everything started with drawing this, no? I mean, so infinite continued fractions in 9 minutes. Okay, so can irrational numbers be approximated? The answer is yes. And actually, for irrationals, the expression is unique. So it's kind of rationals are kind of weird, but irrationals are nice. Okay, relatively, no? I mean, so but the proof of uniqueness. The proof of uniqueness actually is very similar to the proof that for a rational number there are exactly two. Like one there is a kind of a key lemma that one uses in both theorems for the exactly two in the rational case and exactly one in the irrational case. Maybe that's all I'm going to say about the uniqueness. Lang does it like in very nicely. And then let's say for existence, I would say that existence is already done from what we did when we produced, the infinite sequence of rational numbers approximating alpha. Very well. I would say that in those considerations, the existence is done. Because now, of course, you are going to have an infinite stripe, but you can have your alternations of fans. But that stripe is exactly what we considered for this infinite sequence of P and Qn. Okay. Now, of course, that's not very practical because it relies on knowing on knowing all the edges crossed from beginning to end. So it's kind of it solves the existence, but it's okay. But then if you give me, a rational number, let's say square root of 2, what do you do? And so one way to try to do it in practice is say, okay, try to do what you do. Try to implement Euclid's algorithm. So this is yet another question, but for the existence, for the computation in practice, is one does the following. So going back to the very beginning. Yeah, even here, you see here we started with the rational number and started and considered this, right? And then the thing is, this sequence ended from Euclid's algorithm. But written this way, one realizes that A0 has to be the integral part of this one. This we noticed anyway. But then we also notice that, no, look, A1 is also the integral part of this one minus this one. And then A2 has to be the integral part of this one minus this one, etc. So that's how you can start. You can say now take your irrational number and define A0 to be the integral part, and then take x. Sorry, and then this one is a number. I'm getting a bit confused. One second. Sorry. Yeah. To take. Sorry. Start with your irrational number. Take the integer part. Yeah. And now define this one to be the difference x minus its integral part, and take its inverse. And for the inverse, take integral part, and define this one to be the difference. Invert, and for this one, integral part, and keep going.
But in some way, this is tautological, right? Because you're sort of approximating your rational number closer and closer by rationals by using the knowledge of its integral parts, which assumes an approximation that you have beforehand that actually gives you this integral.
Yes, exactly. It's like, yeah, exactly. If I give you an irrational number, I give you an irrational number, let's say a root of the polynomial x to the fifth minus 3x squared plus 5x plus 1. I know it has at most 5 roots. Take one of them, do it. Right? I mean, yeah, of course, it relies on knowing something about the number.
Like even for pi, for example, okay, we know.
You know that it's 3, that it starts with 3.
But
yeah,
like you need to prove.
Exactly. Yeah, and if your intention, like, and this you see is a lot. Well, not a lot. I don't know if a lot, but you see some answers in like Stack Overflow or Math Overflow or whatever. That is like, okay, so guys, how can I compute the continued fraction of an arbitrary number? And then say like, okay, take the decimal expansion, and from there you can start like, yeah, it assumed if I want to approximate it, it's because I don't yet know an approximation, right? So it's like, okay, no, it's just from knowing a property of the number. So yeah, in general, it tells you something that maybe you can do, but again, it's like, but at least it works sometimes, right? Because, for example, for square root of 2, well, for square root of 2 we can, right? Or did I do it correct? Yeah. Did I do it correctly? Did I do something wrong here? Yeah, sorry, here I'm getting confused.
A0 is 1. And your x is 10, I think.
Yes.
A0, like that.
Yeah, I did something very strange here.
Because then you put
Yeah.
1 over x,
Yeah.
0 minus a0, and you put a0
Yeah.
equal to 1.
Yeah.
So,
Yeah. Okay. Anyway, so here. Yeah, I did something very strange.
0 is the integer part of 1 plus square root of 2.
Yes.
So the integer part of 1 plus square root of 2 should be 2. But I don't know why you're taking 1 plus square root of 2.
Yeah.
I think it should just be root of 2.
Okay. Anyway, so here I did something that I think now I don't quite I'm not quite understanding what the okay.
Yeah, maybe
I think I really was focusing on this.
Yeah, exactly.
you take 1 over square root
Yeah,
of 2 minus y, and
Yeah.
well, it's not.
Yeah. Yes, which would tell me for this one you have 2 2 2 2 2 2 2 2 2.
Yeah.
So for this one then you would have 1 2 2 2 2 2 2 2 2 2 2.
Right.
Yeah.
Right.
Yeah.
Oh,
Yeah.
okay.
And
You saw this by doing 1 plus square root of 2, and if you did the same thing with square root of 2, you would not have gotten.
I guess I would have taken a bit longer to realize what the pattern was.
Because from there,
Yeah, and then for the golden ratio, yeah, okay. So just let me say. So something that I didn't discuss is that every infinite continued fraction converges to a real number. So one has a bijection between the irrationals and the infinite continued fractions. Right, and this is what David said, right? I mean, okay, it does the job, but does it really do it? Right? So, and I think for pi it's not yet known. I think, yeah. For E is already a theorem. I mean, for E it's really, yeah. Yeah, and then it's not. I mean, rationals are the new integers, right? Because rationals are the finite continued fractions. Who are the new rationals? I mean, who are the eventually periodic continued fractions? I wanted to talk about this, but I think I'm not going to because I'm running out of time.
What is the answer?
It's the quadratic irrationals.
Oh, okay.
Okay.